trees and graphs terminology. When we refer to trees in computer science, we usually actually refer to what is named rooted tree. Because only in a rooted tree we say what is the node that is the root. And when strictly saying a tree in computer science and in graph, then the only restrictions on the graph that we mean are that it's an undirected and has no cycles. Okay, so a tree is undirected and has no cycles. And if we want a direction in between on the edges, in between the nodes, then we could have what is named a out tree or in tree, depending on the direction of the edges. So we have trees. We have rooted trees where we say this is the root, then we have out trees, and we have in trees. A DAG, a directed acyclic graph, is very similar to a tree. In a tree we said we have undirected and no cycles. In a DAG we have directed plus no cycles. Okay, so the only difference between a tree and a DAG is that on a standard tree, not a rooted tree, then the only restrictions that we have is that the edges are undirected and that there are no cycles. Once you add a direction to the edges on the graph, then it's directed with no cycles, and this is a DAG. This is the directed acyclic graph. So you can refer to a tree as an undirected acyclic graph, or UAC. My term. Graphs are very useful. Practically in every area, whatever you look around, look straight forward, you would see graphs. Okay. Did we have a major crisis lately? Let's think about it. Yes, the coronavirus. So the coronavirus, let's say we pinpoint the first person who had the coronavirus from the animal, and this could be our root. And then we can draw directed edges from this person to the person that he has infected, and from these people to the people that they have infected. So now we have a rooted tree. And if a person cannot infect the previous people, then we do not have also cycles. So basically, the best thing and the best part about graphs and trees is that it's a data structure that can practically be applied almost to anything. Okay, the directory structure, almost anything can be thought of as a graph, can be modeled as a graph. And in the graphs, so we have like weights for graph, we have directed, we have undirected, and those special types of graphs that we mentioned are the tree, the rooted tree, the out tree, and the in tree. There is also what is named in the terminology of graphs a bipartite graph. A bipartite graph is where you split the nodes into two. So let's say let's take a random example from daily life. Let's say you have aircrafts, okay? So let's say you have aircrafts and you need to match the missiles into the aircrafts. Okay, so you can put all the aircrafts on the left side and all the missiles on the right side, and then you can draw lines from the aircraft to the missiles, and then you would be able to tell which missiles match which aircraft. And then there is the term of a complete graph. A complete graph is where every pair of nodes has an edge. That's it. So we usually think of graphs, what we think about is the way that we traverse them, the way that we look at them. But I think one of the most important things is how do you store them? When you need to store a graph on the disk or load it from the disk or from memory or from whatever data structure that you have, then how do you actually store these graphs? So you have multiple ways. So basically, we said that graphs are a collection of nodes and edges between them. So I could describe a graph by saying this node is connected to this node. Okay, so it could be a triplet. Node A, node B, and the weight of the edge in between them if it has a weight. If it does not have a weight, then it would be just a tuple of two items, node A and node B. So we could just have this collection of items. The best thing about this is that it's very simple. So you just have a collection in between the nodes that you connect, in between the vertices that you connect. One of the disadvantages of this is the fact that if you want to find something, whether some node is connected to another one, then you need to scan the whole list. Okay? But so if you want to have a quick lookup, then you could maybe have a map. Okay, map from each node, so you can get this node immediately. And then you would just have on the values of the map the list of nodes that it's connecting to, whether it's directed or indirected, and you could also have the weight there. Another way to represent this is like a matrix. You have a table where on the columns you have all the nodes, and also on the rows you have all the nodes or vertices, no matter how you call them. And you could just place the weight on each cell of this matrix if a node is connected to another one. So there would be like a mirror if it would be undirected, but if it's directed, then you would just have a single point. Okay, so you can have multiple ways of storing them. With a matrix, if you have only one node, if you have only one edge and you have many vertices, then there would be a lot of waste of space. In the list, if you just describe the connection in between the nodes, then it's space efficient, but it would be hard to look for the edges. So in general, we describe the general terminology of graphs, which is what is a tree. We said that it's undirected and has no cycles. Then we said that what we usually refer to as a tree is a rooted tree, where we point and we say this is the root. We have a DAG, which is very similar to tree. A tree does not need to be directed. Okay, it could be just a connection in between the graphs, but a DAG is connected and also is directed and also has no cycles. So they are very similar. Tree undirected, and DAG also has another restriction on this, that it's directed. We said we have out tree and in tree, depending how the nodes point to each other. We have the rooted tree, if we point to a specific node. We have a bipartite graph, a complete graph. And how we store graphs, we could just have a list of the connections in between the vertices, or store them in a matrix, and each one with its own advantages and disadvantages. And this is like the basic terminology into graphs and trees.